Multivariable Calculus, Section 14.7, Stokes Theorem. There's Mr. Stokes, dapper young man. Ireland Uberalis. From Wikipedia. Sir George Gabriel Stokes, 1890 to 1903, was a mathematician, physicist, politician, and theologian. Born in Ireland, Stokes spent all of his career at the University of Cambridge, where he served as the Lucasian Professor of Mathematics from 1849 until his death in 1903. Stokes published his first papers on fluid motion and the steady motion of incompressible fluids, 1842 and 1843, and his work on the friction of fluids in motion and the equilibrium and motion of elastic solids in 1845. He worked on fluorescence, he originated the term, used it in the study of ultraviolet light, and demonstrated that quartz, unlike ordinary glass, is transparent to ultraviolet light. He was an advocate of the wave theory of light. A crater on Mars is named after him. Enough of the history lesson. Review of Green's theorem. If C is a positively oriented, smooth, or piecewise smooth, simple closed curve that is the boundary of a region R in the xy plane, and functions P and Q, the components of vector field F, have continuous first-order partial derivatives on R, then the line integral of f dot t ds is equal to the line integral p dx plus q dy, which equals, and here's the big part of Green's theorem, the double integral over R of the partial derivative of q with respect to x minus the partial derivative of p with respect to y dA. Now notice that TDS is dr, which equals dx dy, which makes it obvious why the second line integral is equivalent, t being tangent to the curve, and ds being the instantaneous change along the curve. And so here's a picture of a region R in the xy plane, and C is the curve that goes around, that forms the boundary, and it's counterclockwise, positively oriented. And that line integral, then, of f dot TDS is equivalent to the double integral, where you're integrating the quantity shown in the integrand there on the right, all over the region. And so you're integrating these lengths at each and every point. Now you can think of a normal vector coming out of the xy plane. That would be k, right? And so the work done by F, which is P comma Q along C, is like integrating the curl F dot n over R, because the partial of Q with respect to x minus the partial of P with respect to y is the third component in curl, and it's the only one when you're operating in two dimensions. That would be the only component. And if you dot it with K, then that's what you get. So Green's theorem is a two-dimensional line integral, which can be written or equivalently, or can be evaluated equivalently by an integral over a 2D region, a double integral. And Stokes' theorem is going to be a 3D line integral shown to be equivalent to integrating over a 3D surface, and the same kind of thing involving the curl. So again, this is the component of curl F in the k direction. So Stokes' theorem says, given an oriented, bounded, piecewise smooth surface S in space with positively oriented boundary curve C, unit normal vector n, T a positively oriented vector field tangent to C, and vector field F equal to PQR, three components this time, continuously differentiable in the space region containing S, then the line integral F dot TDS is equivalent to the double integral of the curl of f dotted with n ds. And so it's actually the same, except n is going to have 3 components instead of just 1. Heavy lifting here. Now notice it says any surface bounded by the curve C. So if there are choices, you want to choose the simplest surface that C binds. For example, if that's the boundary curve C, the simplest surface would be a flat one on the xy plane. But you could, if you were, wanted a challenge, you could use a cone or a hemisphere or any other surface that C was the boundary for. Okay, so there's the crux of Stokes' theorem right there. Work done by F along C equals the value of the double integral regardless of the surface used as long as C is the boundary of S. Okay, so here's a more general surface. It looks kind of flat, but I meant for it to just be, three-dimensional. And there's a picture of T, tangent to the curve, and N, perpendicular to the surface, and then N cross T, positively oriented. What does that mean? That means that if you are standing on the curve, you should be up, facing upwards the same as the normal, and you would see the surface on your left. So there goes Mario around. That wasn't quite right, but that's more or less what it looks like. As he walks around, the surface is always to his left, and he's standing up the same way as N is. Someone walking along the boundary curve will see the surface to their left and N pointing upward, same as their body. So that's what we mean by positively oriented. Work done by F along C is equal to the curl of F dotted with N integrated over the surface. That's Stokes' theorem in words. Quiz. Identify the direction of C and N for each positively oriented surface below. So here we have a cylinder. It actually has 2 boundary curves. The upper one is like that. Mario would be rotating with N shown by the thick arrow, and he would see the blue surface to his left. Now the bottom curve then goes the other way, and there's Mario walking around, and again he would see the blue surface on his left. How about this one? Yeah, it's kind of the same as the first one, except Mario and the normals are tilted a little bit this time. But he would see the cone, the blue cone on his left. Okay, let's review curl. Given differentiable component functions p, q, and r such that f of xyz equals p of xyzi plus q of xyzj plus r of xyzk, the curl of f is defined as del cross f, and there's the determinant, which is what I use to evaluate it. You just add 2 more columns and do the arrow stuff. And it's bottom minus the top, or if you've got the formula handy, this is what you end up with after all that computation. And notice that the third component is the one in Green's theorem. So the first 2 are 0 in 2 dimensions, leaving only that third component in Green's theorem. But in Stokes' theorem, we're going to have all 3. All right, some curl trivia. If F measures the velocity of a medium, then curl F measures how much rotation there is in that medium. The direction of curl F corresponds to the axis of rotation, and the magnitude of curl F is twice the angular velocity of the medium. Now, we don't really deal with this in the calculus, but you'll run across things like this in physics. All right, proof of Stokes' theorem. I'm not actually going to prove it, but I'm going to sort of show you how it's proved. Okay, so here's the idea. Green's theorem is just a special case of Stokes on the xy plane. We could show Green's theorem is also true on the xz plane, the yz plane, and in fact any plane. Any surface area can be approximated by little tiny flat parallelograms, which, when taken to the limit of infinitely many, infinitely small parallelograms, will equal the actual area of the surface. It's just that the parallelograms are tilted as we go along. So here's a picture of a surface, and you could cover the whole thing with little parallelograms. Okay, proof of Stokes' theorem again. I'm going to cop out here because it's very long and tedious. If you really want to see it, here's the link. I'll be glad to email that to my students if they want it. And if you, this is on the MIT lecture series, and if you will just forward to 33 minutes and 14 seconds, the professor will prove Stokes' theorem for you in great detail. Now there's a connection here with conservative vector fields. Recall that independence of path, conservative fields, and vector field f equaling a gradient of some function, where f is called the potential function, are all equivalent. And that if f is conservative, then work done by f around any closed curve comes out to 0 because it doesn't matter what path you take. So if you just stop and start in the same place, obviously that work is 0, right? Now we will show that conservative fields also have their curl equal to 0, the 0 vector, and vice versa. And this one I will prove. Part 1 will show that if curl f is the 0 vector, then f is conservative. And part 2 of the proof, to go the other way, will show that if f is conservative, then curl of f is the 0 vector. Ready? Here we go. Part 1, show that if curl of f. So part 1, show that if the curl is a 0 vector, then f is conservative. Here we have any old points a, b on any old surface with two different paths from a to b, c1 and c2. We're going to assume that the curl is the 0 vector. That means that the double integral over the surface S of curl f dot n is going to be 0 because we're dotting the 0 vector with n, so no matter what n is, we're going to get 0. And if we integrate 0 over any surface, we're going to get 0. Now let's see be c2 followed by the opposite of c1, which would take us from a to b and then back to a. And so by Stokes' theorem, we know that the line vector f dot t ds is going to equal the double integral of curl f dot n ds. And we established that that is 0. Now we can rewrite the line integral of f dot t ds as the sum of the two integrals following c1 from a to b and then the opposite of c2 back to a. So we have the difference of those two integrals equaling 0. Now if the difference is 0, that means that those two integrals are equal. And since the path from a to b didn't make any difference, we get the same value. That establishes independence of path for f. And independence of path is equivalent to being conservative, and therefore we have shown that if we assume the curl of f is 0, the 0 vector, then f has to be conservative. Now we're going to go back the other way. We're going to assume that f is conservative and show that the curl then has to be the 0 vector. So we're assuming f is conservative, and that means that f is the gradient of f for some little function f, potential function, and the potential function is made up of the three partial derivatives. Now remember then that that means the partial with respect to x is p, the partial with respect to y is q, and the partial with respect to z is r when we use this formula for the curl f. So if you plug into that formula, the curl of this gradient vector, which is f, is going to equal this quantity right here. Okay, so take a minute to check that out. See if you agree. Okay, now from previous section, we know that f, the partial derivative of u, then taken again with respect to v, is equal to the partial derivative of f with respect to v and then taken again with respect to u. These are second derivatives if the field is conservative, which it is. So if you look above, then all three of these quantities in our curl of the gradient vector are going to be 0. Therefore, we've shown that the curl is the 0 vector. Hence, if f is conservative, then the curl of f is the 0 vector. So now we've proved it both ways, and we can state that the curl of vector field f is the 0 vector if and only if f is conservative. Ta-da! Irrotational vector fields from Wikipedia. A vector field f is said to be irrotational if its curl is 0, that is, if del cross f is a 0 vector. For this reason, such vector fields are sometimes referred to as curl-free vector fields or curl-less vector fields. So here's an example of a vector field, xi plus yj. This is in 2 dimensions, and so the curl is only going to have one component, namely the partial of q with respect to x minus the partial of p with respect to y. So in this case, p is x, so the derivative with respect to y is going to be 0, and q is y, and so the derivative of q with respect to x is going to be 0. So we get 0 vector for the curl. Therefore, this is an irrotational vector field. And you can kind of look at it and say, well, you know, it's not rotating, that's for sure. No curl there. It won't always be that obvious just by looking at it. Let's look at another example. This one has some constant times negative yi plus xj. And so q is x, and its derivative will be 1, and p is negative y, so its derivative will be negative 1. And so we get 2k, which is not the 0 vector. Therefore, this is not a curl-free zone, not a curl-free vector field, and it is not irrotational. It's kind of a double negative there. Okay, one more example. This one is, I don't know. What do you think? All right, so derivative of q with respect to x, that's sine y, so that's going to be 0, and derivative of p, which is sine x, that's going to be 0 with respect to y. So this one is irrotational, curl-free, conservative, aka independence of path, etc., etc., etc. Let's review. Here's Green's theorem. Take a look at that. Looks familiar. You got the one component of curl there. Here's Stokes theorem, abbreviated. And equivalent statements is to say that a field has independence of path, to say a field is actually a gradient field, to say it's a conservative vector field, to say it's an irrotational vector field, or to say that its curl is the 0 vector. Those all indicate the same quality in the vector field F. Okay, some examples. In 1 through 5, use Stokes theorem to evaluate this double integral of curl dot n ds. Okay, so if they want us to use Stokes theorem to evaluate the double integral, that means they want us to use the line integral. Okay, so for number 2, here is our vector field, and S is the part of the paraboloid z equal x squared plus y squared below the plane z equal 4, and with upper unit normal vectors. In other words, they want it to be positively oriented, and that's what we'll do. So I have to have a picture. Need a picture. There's my paraboloid. And here's our line integral that we're going to need. And obviously, when we have a line integral, it's a single integral, so we need to get everything in terms of one parameter. Here is the boundary curve for the surface. And what's its equation? Well, if z is 4 there, then you just put that 4 in for the paraboloid, and you get 4 equals x squared plus y squared. So how do we parameterize that? Well, with circles, it's easy. We just use r cosine theta for x and r sine theta for y, and in this case, r is 2. And then z is always 4 on this particular curve. So note that its derivative will be 0. So now we got to plug into our line integral. P is 2y, so that's going to be 4 sine t. Q is 3x, that's going to be 6 cosine t. And then dx is going to be derivative 2 cosine t, which is negative 2 sine t. dy is the derivative of y, which is going to be 2 cosine t. So putting all those into our line integral gives us that. And we just drop off that last term. Yay! So now we have to simplify that, and note that t goes all the way around the circle from 0 to 2 pi. And then we need identities for cosine squared and sine squared. And then we collect like terms and then integrate. Okay, so not too bad. From 0 to 2 pi. Now notice that sine of 2t is going to be 0 at 2 pi and 0, so that term goes away. And we just have 2 times 2 pi minus 0, which is 4 pi. Okay, let's move on to number 4. Different vector field. And S is the part of the cylinder x squared plus y squared equals 1 between the planes z equal 1 and z equal 3, again with outer unit normal vectors. In other words, we have to do a positively oriented, and it will be because we're doing the line integral. There's our line integral. There's our cylinder, but this time we've got 2 boundary curves, C1 and C2. So we need to do 2 line integrals. Let's start with C1. Well, here's both of them. For C1, z is 1, and for C2, for C1, z is 3, and for C2, z is 1. But they're both circles with x squared plus y squared equals 1, and so r cosine t for x and r sine t for y, r is just 1. Okay, so let's fill in, let's do C1 first. So we have for P, yz, which is sine t times 3, and then dx is the derivative of cosine t negative sine t. Then the middle term, Q, is xz, so that's cosine t times 3. And then dy is cosine t dt. And then for the last term, we have xy times the derivative of z, which z is constant, so that's 0. And I didn't bother rewriting x and y in terms of t because that term's going to be 0. So bring the 3 out front, and we get cosine squared t minus sine squared t, which is an identity. Yay! So that's easy to integrate. From 0 to 2 pi, that's going to be 0. Now we'll get the same result of 0 from integrating along C2, because the only thing it changes is the 3 becomes a 1. So that's going to be 0 also. So the answer is 0. 0 plus 0 equals 0. Note that this means that curl f is 0, and f is conservative, and f is irrotational, etc., because the line integral is equal to the double integral, and so the double integral will be 0 also, which makes the curl 0. All right, for numbers 6 through 10, use Stokes theorem to evaluate this line integral. So this time we're going to be setting up the double integral and evaluating that. So here's the vector field, and the curve is x squared plus y squared equals 9, where z is at 4, and it's oriented counterclockwise. So let's take a look at that. Counterclockwise, the arrows indicate that. But it is nice and flat, so that's good. Here's our integral, and we have to compute the curl. So there's our determinant that I used to compute curl, and I replace the middle row. The top row is I, j, and k, and the middle row is the partial of x, partial of y, partial of z, and then the bottom row are the components of f. And then I add 2 columns, copying the first 2 columns, and if I take that diagonal, I get 3i, because the derivative with respect to y of 3y is 3. And then I'm skipping the j one because the derivative of 3y with respect to z would be 0, so I didn't bother writing that. And then the next one, the derivative with respect to x of negative 2x is negative 2, and that's times k. And then going upwards, we get 3k, but the next two are 0. So that's all we have there. Now notice that over on the picture, see the arrow? See the arrow? See the arrow? That's going to be n, and obviously that's just k, right? So, and remember, little Mario would be walking around with his head pointing up the same way as the arrow, and he would see that surface to his left. So n is k. Now the curl then, when I could take the bottom 3i minus 2k and subtract the top, I get 3i minus 5k. The j component is 0. And n is just k, 0, 0, 1. And when I dot those, I get negative 5. Woohoo! So that's our integrand. And r is just that circle, and it's flat. So we can change ds to dA and integrate over r. And since it's circular, best thing to do is to switch to polar. And r goes from 0 to 3 because it's x squared plus y squared equals 9. So the radius is 3. And then dA becomes r, dr, d theta. Don't forget the extra r. And we're going all around the circle, so theta goes from 0 to 2 pi. So we integrate that with respect to r and evaluate from 0 to 3. And then we integrate that from 0 to 2 pi. We get a negative 45 halves theta from 0 to 2 pi. And the 2 cancels. So we get negative 45 pi. Number 8. We have our vector field, and this time the curve is a triangle with these 3 vertices, again oriented counterclockwise. So there's a picture of the triangle with the 3 points in red. Made them a little large, didn't I? And there are actually 3 curves then, one for each side of the triangle, C1, C2, and C3. And there's the integral we need. So now we're going to need the curl, and we're going to need the normal unit vector, unit normal vector. And so to get the normal vector, what I decided to do would be to create a vector from 0 to the point 0, 2, 2, and another vector from 0, 0, 0 to the point 2, 0, 0, because then I can cross those 2 vectors, and that'll give me a vector perpendicular to the triangle. So to get n, I crossed those 2 vectors. I did not show the work. You could do that on scratch paper if you like. And then we need it to be a unit vector, so the length there would be the square root of 16 plus 16, or square root of 32, or 4 root 2. And so the 4's cancel, and we get 1 over root 2 times the vector 0, negative 1, 1. Okay, so then we also need the curl. So filling in the components of the vector field along the bottom, notice that all the downward arrows, oh, and adding 2 columns there, all the downward arrows are going to lead to 0 because we're taking the derivative with respect to one variable that is not in the component. Going upward, we get 1 times k, 1 times I, and 1 times j. And it's the bottom minus the top, so our curl is going to be negative 1, negative 1, negative 1. So now we need to dot the curl with n, and that comes out to 0. Yay! So our integral is just going to be 0. That was too easy. Number 10. Here's our vector field. And C is the intersection of the plane, z equals y, and the cylinder, x squared plus y squared equals 2y. And there's the integral we're going to need. Now, our cylinder, in order to draw that, I'm going to bring the 2y to the left and complete the square by adding 1 to both sides. Now I can see that the base of that cylinder is a circle centered at 0, 1. With radius 1. So here's my beautiful picture. The surface, or the curve C, is that red curve. And so the surface is tilted, sort of an elliptical section of the plane z equal y. And then the shadow of that section of the plane is the circle R on the xy plane. So we're going to need the curl, and put the components of f along the bottom, copy the first two columns, and all the downward arrows are 0 again. So we get 2yk going up, and then 2zi going up, and then the last arrow up is 2xj. And again, it's minus the top, so that's going to be negative 2y, negative 2z, negative 2x. Oh, not in that order. Okay, now for the normal, it's actually pretty obvious, isn't it? Because there's no x component, there's no I component, and it's pointing upward and to the left. So to make it a unit vector, we need 1 over root 2 times the opposite of j plus k. Okay, so now we're going to dot the curl with n, and that gives us root 2 x minus y. So we need to integrate that over the surface. Now we are going to have to do some calculations here using this from a previous section, because z is actually just a function of x and y. So we can use this integral to change our surface integral into something manageable. So here's what we've had so far from the last page. Now we're going to fill in our integral. We still have root 2 times x minus y, and then fortunately the partial of h with respect to x is 0 because there's no x in our h formula, and the partial of h with respect to y is 1, and so we get a nice square root of 2 for our changing from ds to dA, and so the root 2 times root 2 becomes just 2. Now I'm going to change to polar. I might have buyer's regret for doing that, but notice that our original formula for the cylinder was x squared plus y squared equals 2y, and changing that to polar form we get r squared equals 2r sine theta, and then dividing by r we get r equal 2 sine theta. So on that green area down there, the circle, r is going to go from 0 to 2 sine theta, and theta, now this is tricky, theta is going to go from 0 to pi because that whole circle is in the first and second quadrants. So we bring the 2 out front, theta goes from 0 to pi, r goes from 0 to 2 sine theta, x becomes r cosine theta, y becomes r sine theta, and then dx dy becomes r dr d theta. Don't forget the extra r. So then I took the r out and combined it with the other r, so I got r squared, and then integrated with respect to r, which would be 1/3 r cubed. And so the 1/3 r, the r cubed is 2 sine theta cubed, so that's 8 sine cubed. I took the 8 out with the 2 and made it 16/3. Oh boy. So this would be easy because that's just going to be the antiderivative there is just going to be 1/4 sine to the 4th theta, since cosine theta is the derivative of sine. But sine to the 4th theta, we'd have to use the identity 1/2, sine squared equals 1/2 minus 1/2 cosine 2 theta. We'd have to square that, and then we'd have to multiply it out, use another identity, and I don't think I feel like doing that. You may if you wish. I copped out, used the calculator. And the answer is negative 2 pi. Number 12. Show that this vector field, blah-de-blah-de-blah, is irrotational. Oh, you got all kinds of ways of showing this. You can show that the curl is 0. You can show that it's a gradient vector field, blah, blah, blah. Okay, so we'll do the curl, since that's kind of the new thing, right? And I didn't write all those in there because they're too huge, so I just looked at them. The derivative of the first component with respect to z is negative 20xz, and that's times j. And then the derivative of q, which is the second component with respect to x, is just 9y squared, and that's times k. Oh, notice that the first one with the I and the r, there is no y in the third component. That's why I didn't bother with that one. That one would have been 0. Okay, this one, P, is the first one, and with respect to y, we get, would that be 9y squared? Yep, and that's times k. And then Q doesn't have a z in it, so I skipped that one. And then R, derivative of R with respect to x would be negative 20x z, and that's times j. Oh, looky there. Wow. They're the same, aren't they? So look what we get. Woohoo! 0. And therefore, the vector field is irrotational because its curl is 0. Or, maybe this would be easier. Let's just show that F, vector field F, is the gradient of some function f. Would that have been easier? Okay, so fx is the first component, and that means if we integrate that with respect to x, we get 3xy cubed minus 5x squared z squared, and then there could possibly be a term with just y and z in it. And then fy is the middle term, and if we integrate that with respect to y, we get 3xy cubed, plus possibly a function in terms of x and z. And so far it matches, right? Matches our previous one. And if we look at the third component as the derivative with respect to z, then when we integrate that, we get negative 5x squared z squared, plus possibly a function in x and y, and that one matches. And so therefore, the potential function exists, namely 3xy cubed minus 5x squared z squared. That could be the potential function, and hence this vector field is irrotational. Okay, in most of these exercises, n was fairly obvious. What if it's not fairly obvious? What am I gonna do? I don't know what n is. Well, recall that the gradient for g, x, y, z is z minus f of x, y, aka the gradient of g is negative f sub x minus f sub y, comma 1, and will be perpendicular to the surface of z equal to f of x, y. Okay, that's from a previous lesson. So, n will be plus or minus gradient g divided by its length, depending upon whether n points upward or downward. You would need the plus or minus sign. Or you could just switch the gradient, take the opposite of the gradient. All right. I saw this joke somewhere, and I thought it was kind of cute. The more complicated the math, the dumber you sound explaining it. Stokes Theorem? Yeah. That's how if you draw a loop around something, you can tell how much swirly is in it. It's kind of accurate, but not very technical. Enjoy your homework. Bye-bye for now.
If seeing is believing, and Stokes was a genius, think about comparing curves and surfaces. F dot T D small s, and curl F dot N D big S. One might integrate easily, while the other's quite a mess. Stokes is a theorem I really like, a theorem I really like. Stokes is a theorem I really, really like. Of course, Stokes only works if C is the boundary of the surface in its entirety.